Okay, welcome back everyone to afternoon and the last talk of the week. And I guess we saved hopefully the best for last, so we'll find out, Eric. I think so. Eric's going to tell us about the complexity of topological amplitudes. And yeah, put on the mic. And you got to flip the button.
Yes, I will.
Yeah.
I have the exact same.
Cool.
Cool. Everyone hear me okay? In the back? Yep. Ooh. Everyone hear me? Too loud? It's very loud to me. Okay, cool. So, yeah, thanks for the opportunity to speak to the organizers. So I don't know if I'm doing myself any favors by mixing up the format right at the very end, but you know, I'm a mathematician, so I want to give a chalk talk. So here we go. So the big goal, yeah, I get some feedback here. Let's turn this down. I don't know if I can. Okay, so the big goal here is I want to characterize precisely the 2+1D topological order that can be used for universal quantum computation in the topological quantum computing paradigm. And the key word here is universal. So TO is topological order, TQC is topological quantum computing. And I want to stress, no bells or whistles allowed. So what this means is, you know, there's been a lot of very cool work in recent years where ideas from topological phases, you know, have led to better codes, things like this. But, you know, these have a bunch of bells and whistles like boundary conditions and defects. And I don't want any of that. I want to go back to what people did 20 years ago when topological quantum computing was first kind of described, where you braid anyons. Okay, so this is what you might call the OG. OG is for original gangsta, right? So TQC paradigm via anyon braiding. And as I said, no defects, domain walls, etc. And like all of my operations have to come from the TQFT, from the topological quantum field theory, because those are the things that are topologically protected. So, so like no magic state injection. So to be sure, with all of these constraints, what I am trying to do will not get us any closer to fault tolerance any sooner, right? All of these extra bells and whistles have led to great constructions that will ideally get us to fault tolerance sooner than otherwise. But this I think of as an important fundamental question, right? About in characterizing the intrinsic computational power of different topological phases. Okay, so now I'm not really, I'll wax poetic about this at the end of the talk, but as the title of my talk indicates, I'm not really going to address this directly. I'm going to look at a warm-up to this question. So today, we'll explain recent progress and I'll explain in what sense this is a warm-up. And so you can think of this warm-up question as the problem of computing topological amplitudes. And I'm saying that just to try to fit things into the topics these days. But really, it's the equivalent to computing partition functions in a given topological order. So precisely, or maybe somewhat more precisely, I'll make this even more precise later, is given a topological order, and I'll explain what I mean by that. And when I say TO, I mean 2+1D TO. Okay, so so how hard is it, or you know, what is the complexity of the problem of computing the kind of native topological amplitudes inside that TO? Okay. And you know, if you prefer the language of partition functions, well, that's also what I'm doing. And I'm going to add on an important word at the very end here. I want to compute these numbers, these amplitudes, exactly. Which is a little bit of a weird thing to ask, because amplitudes aren't like directly observable things, right? Typically, we only can approximate amplitudes by repeated measurements. But you'll see why in a moment, though, like because this really is a warm-up to that, it's worth trying to understand this first. Okay. So, great. So let me give some background. So this table will show up later, maybe in 25 minutes. Okay, so it's a mystery for now. Just a table of examples that we'll discuss.
Sorry, so
Yep.
you're assuming you have a couple of the quantum computer.
I'm going to tell you what I mean by that precisely in just a moment here. Yeah, great. Yeah. So here's my background. So, you know, like I said, I'm a mathematician. If you ask me to define what a 2D topological phase of matter is, I'll tell you it's a TQFT. Okay. So there's a 2 + 1D TQFT. I guess I'm using capital D, TQFT. And so, you know, there's some amount of physics involved, and whether this is the correct definition, I don't want to split hairs over that. This is my definition. So it's whatever, some type of physical system described by a TQFT, and maybe in low energy. And now in this kind of yoga, like the topological order is described by a modular fusion category, which is some type of algebraic data that we think of as the package that describes the topological order. It's like all of the quantum numbers that, you know, you need to understand in order to determine what phase of matter you're in. Okay. And now, so these two things, I'm not going to fuss about them. What's important for me is that these are the same. Okay, this is a theorem of math, right? So they're the same via what's called the Reshetikhin-Turayev construction. And so, you know, Reshetikhin and Turayev explain, given one of these algebraic gadgets, how do you write down a TQFT? And then many years later, about 10 years ago, some mathematicians proved that, in fact, every 2 + 1D TQFT with enough adjectives, oriented, once extended, semi-simple, comes from a modular fusion category. So these are basically the same thing. Okay. And now, so when I say given a TO, given a topological order, what I mean is given explicit data for a modular fusion category. So topological phase of matter. Yeah, sorry. Yeah. So 2D, like 2 is like the spatial dimension of the matter. Yeah. So given a TO means, and I'll call this modular fusion category throughout the talk script B, because it's a fusion category that's braided, and we'll talk about some examples of these in a minute. So given a TO means given what's usually called skeletal data for a MFC. Skeletal. For B. And so this means things like F symbol. Well, you have the fusion rules. These are like the first, most basic data. So we have the fusion rules, which are some integers, N, I, J, K, F symbols, R symbols. Like an F symbol would be like F, I, J, K, L, something like that. Maybe in full level generality, I need 10 J symbols. So, you know, maybe I need alpha, beta, some other things, whatever. There's some other things. These are some algebraic numbers. So Q bar is the field of algebraic numbers. And what I have in mind is that these F symbols and R symbols, you know, R symbols are in here as well. J, K, so, you know, algebraic numbers, they're a subset of the complex plane. They're a dense subset of the complex plane. So but it's countable. So what are algebraic numbers? They over Q. They are roots to equations with rational coefficients, right? And even though this is like, It's kind of gnarly. This is a finite, like describing a single element of Q bar is a finite data, takes a finite amount of data. You just have to know like what's its minimal polynomial and like a little bit of extra data to distinguish the different Galois conjugates. Okay? And like you can actually work with algebraic numbers explicitly symbolically on computers. Okay? So I'm assuming I have all this data given to me when I have the TO. Okay? And then so, yep. Because I might as well, because I'm in a fixed topological order. This is a good question. And Achnianu rigidity tells me that if my fusion rules, any solution to my fusion rules for F symbols and R symbols, there's a gauge equivalent solution that is expressible as algebraic numbers. And since I'm working one TO at a time, I might as well make that thing as nice as I can first. Yeah. So an example of an algebraic number is like, you know, the golden ratio, right? This shows up with Fibonacci anyons, right? So it's not a rational number, but, or square root of 2, right? Square root of 2 is a algebraic number, things like this. Other questions about the input here? So yeah, you know, if this might be a little opaque if you're not familiar with these things, but you know, these fusion rules kind of explain how the anyons fuse, and then these F and R, the F symbols explain what the associator data is for these things, and the R symbols explain the braiding, okay, in ways that I'll kind of draw some pictures in a moment. It's not that important. I think the pictures are more important for this talk. So in the anyon braiding, so I told you we're going to use just the like OG anyon braiding paradigm. So let me be precise about what that means. So I need to tell you what our memory is. I need to tell you what the unitaries are on that memory, and I need to tell you what the measurements are on that memory. So you know, and really what we want to do, right? Because we want to know, like, can we perform universal topological quantum computing? So what that means is like we'd like to know, given the data of our category B, like, is there a way to encode like qubits into the state spaces I'm about to describe, so that you can simulate with these operations, I'm about the braiding and such, you can simulate arbitrary quantum circuits. Okay? That's what universal means. So first things first, we need to, in this paradigm, we have to have some basic idea, we have to agree on some basic idea of how we're going to encode qubits, okay? Or QDITs. So we encode a qubit in the state space of a few anyons. So you have a few of the anyons from B, and you say, okay, if I had a few of these anyons like sitting on like a disk, that they have a state space, and inside that state space, I'm going to identify a 0 and a 1 as my qubit. So and so, for example, if I have an anyon, if an anyon A is self-dual, right? Because these particles all have to have antiparticles, so that's something baked into these fusion rules. So if an anyon is self-dual and non-abelian, I can encode a qubit in the following way. So I'm going to use 4 of those anyons to encode a qubit. So I imagine I have 4 of those anyons. They're all A. And they're on a disk. And that disk has total boundary charge, the vacuum. Okay. So this is just, you know, in the actual algebra, right? This picture represents a vector space, right? So it's the vector space of morphisms from the vacuum to the tensor product of 4 copies of A. And so how can I get a qubit in here? Well, I told you I'm going to use, you know, this is just an example. If it's self-dual and non-abelian, then I get a qubit as follows. So I can specify states inside this vector space by putting tangles, by filling it, right? This is just a 2D thing, but I could draw a 3-dimensional picture with a tangle that describes like an anyonic process, right? And so what I could do is take this thing and the following tangle makes sense and is non-zero. So it's an actual valid state, that one. So what is this saying? It's the anionic process where like you start from the vacuum, you create a pair of, two pairs of A and A dual, but A dual is A, so you're good. And like, well, okay, that's a state in here. Okay? And we might think of this as like 0. And then another state I can find using the fact that they're self-dual is this other planar matching state. And I might call that 1. Okay, now I'm lying a little bit because these two states aren't actually orthogonal usually, but they are linearly independent if A is non-abelian. And so you could, this will literally be 0 if you normalize it correctly, but the 1 is a little bit of a lie. You should probably apply the Gram-Schmidt orthogonalization process to find an orthogonal state that comes from stripping away this piece of that state, right? And you call that 1. Right? So it's just a little example. Great, yeah, it comes from all this data. Yeah, so it's easy, yeah, from this data to compute it, yeah. Good question. So and I'm gonna kind of come back to that in a second when I explain what the hell I mean by topological amplitudes, okay? Basically, what I would call, maybe I'll just say it now. So like if I have some anyons on a disk, any way of filling in a tangle will specify a state. And I'm gonna inside the state space. And I would think of that as a topological state because it comes directly from some topological configuration. And if you gave me 2 topological states with the same boundary conditions, I can glue them together, and that's essentially the inner product. And glue them together along their common boundary. That's essentially the inner product, and then that's what I mean by topological amplitude. Okay? But that thing winds up just equaling what's called the partition function as well, so it's not. So, right, so that's how we get a single qubit, for example. So once you know how to get a single qubit, it's easy to get several qubits. You just set pictures next to each other, right? You just take several pictures next to each other. So for example, if I want the state 1, 0, I just take this state, this picture, and I put it next to that picture. So it would be this ket. I would have 8 anyons of A type. 1, 2, 3, 4, 5, 6, 7, 8. And then the first 4 need that correct matching there. And then the other 4 need the other matching. So that ket inside, this is in the state space of my 8 anyons with vacuum boundary charge. Yeah. So this is our memory. Yeah, question?
Why are the 0 and 1 distinct?
Why are these topologically distinct? So I cannot take this diagram and wiggle it while fixing the endpoints to make it look like that. Yeah, you have to keep the endpoints fixed. Yeah, it's a relative homotopy, not a relative isotopy that matters. Yeah, yeah, good question. So, okay. I mean, so those, right, these are equivalent up to some braid, but that braid is a non-trivial braid, right? So yeah. Okay, and with that note, what are our unitaries? Our unitaries are braids, okay? Those are our relevant unitaries. And these are like the elementary unitaries, really. These come from braids. So for example, like in this example, if I have my 2 qubits here, so what winds up happening by the yoga of the TQFT is that I have a representation of the 8-strand braid group onto this Hilbert space. So it's not obvious, but it follows from the structure of the TQFT. This Hilbert space is finite dimensional. And so I get a unitary representation here on that. So if I have 8 anyons, it's the 8-strand braid group that acts. And those are the unitaries I can use. So B8 here, this is the 8-strand braid group. And let me be really precise. So like, so maybe looking at a single qubit gate, like over here, right? The 4-strand braid group is like giving me my single qubit gates. Although, I mean, there's leakage issues you in practice you care about, but I don't care about leakage. So the encoding, you have to deal with that with the encoding. But so over here, we have like a 4-strand braid group that acts. And so maybe I give you the braid that's like something, maybe call it beta. What did I do here? What would normally be called sigma 1 inverse sigma 2. So this braid, how does this braid act on maybe 0, right? So beta acts on 0 by taking this braid, whatever this mystery word is, it's some description of a picture of a braid that I just stack on top of that, right? So, and this specific braid, I read them from right to left. Right is bottom, left is up. So this braid here will act on 0. So I start with 0, but then I do the second braid generator, and then I do the inverse of the first braid generator. And whatever this is now a topological state inside of here, it's different from these two in general. And you can resolve what this state is in terms of these two and other ones because of leakage in terms of the graphical calculus from all this data. Okay. So those are like the elementary unitaries. And then finally, we have to ask what types of measurements do we allow? And the measurements, we're only going to allow charge measurements. So this sounds fancy. There's actually 2 versions of it. It's not that fancy, actually. So there's version 1, probably write it on the next board. It's called destructive measurement. And so first of all, So destructive measurement, we think like, okay, I have 2 anyons. I have anyon A and I have anyon B. And I bring them close together. And when I fuse them, the resulting anyon is not simple anyon. It's in a superposition of the simple anyons according to the fusion rules that I just erased. So when these guys fuse, until I've measured the resulting fused particle, it's a composite over all the other possible anyon types, possibly with some multiplicity. And sorry, I didn't give myself enough room here. So then what I do is I say, well, okay, I haven't done any measurement yet. All I did was take these 2 anyons and put them close to each other to turn them into that thing. But then I can ask that guy, God knows how, I'm not a condensed matter experimentalist, but I could ask that guy I could measure it and say, okay, you're in a superposition, but I want you to pick one of these things. And it will, according to some probabilities, with the Born rule, depending on what state the system was in here to begin with, right? So that's the destructive measurement. And then the other type so this is the charge measurement, and then the other type is sometimes called interferometric. And a bothersome thing about this is that what I did here, I'm not preserving the anyon number, right? Like I had 2 and I turned them into 1, so like that could be a problem. So, but interferometric allows you to perform these measurements without changing the number of anyons around. Okay. So the idea here is like, let's suppose I have a bunch of anyons, A1, A2, AK, and the total charge of all of these anyons can be in a superposition of different charges. So what we can do is send a probe anyon around to measure that. And so now sometimes people talk about this using anyonic beam splitters. Another way to talk about it is just using composite anyons. So what I'm going to do is I can learn some information about what the total charge of these K anyons is by preparing some other anyon P. but it needs to not just be P, it should be in a superposition of P and the vacuum. And then if I take this and wind it around these guys, like this, so I'm creating a pair, right, of like a pair, like a P plus I pair. And I do this, and then I perform the charge measurement here. So the outcome of that measurement will tell me something that I can use to learn about the total charge of these guys. I'm assuming it is, yeah. If it's not, then like Microsoft was doing this for many years. And so is it protected? I don't know, but like they seem to think it was not unsensible, right? So because like, for instance, there's this nice little paper of Mike Friedman and Claire LaValliant where they show that any destructive measurements can actually be simulated like effectively by interferometric measurements. So, there was a long time, there were many years like around 2012 where they were writing a bunch of papers about measurement-based topological quantum computing. And yeah, so they must have thought it was sufficiently fault tolerant. Yeah, but I'm not going to think about that. Yeah, but even though it's a good question. Yeah, so you can think of, the braiding of this composite anion is kind of the same thing as sending P around, but before you do, kind of putting in a beam splitter there that kind of makes it go around in superposition, and then you're doing some interferometry. It's the same thing. Okay, and then the question, this is really the main question, the big question from the beginning of the talk that I've erased. Is, well, given the modular fusion category B, do these operations support universal quantum computing? Okay, and now something this is like a minor point, but it's, I think, worth highlighting, especially because over the years, mathematicians, like Eric Rao, Zhenghan Wang, their collaborators, Julia Plavnik, et cetera, lots of these people, they've thought about this exact question for many years, but they rarely allow themselves to use interferometry, any of these charge measurements adaptively, okay? So what I'd like to do is actually say that there's two versions of this question. One version, we do not allow adaptive charge measurements. You only do them at the end, basically. And the other version, you allow adaptive charge measurements and you use them on the fly. And depending on the outcome of your charge measurement, that'll help you decide how else to braid later in the circuit. Okay. And so, So version one, we know adaptive charge measurements. So, and in this case, if you're not going to do adaptive charge measurements, you have to know something very strong about this braid group representation. So if they're going to be universal. So let me say universal in this setting kind of implies certain density properties of these representations. I'm going to be a little vague about that. I'm going to be vague about that because it's the next thing that I think is the better question, frankly. So, yeah, so maybe I won't bother writing this, but I'll repeat what I just said. My 2 cents, question one is a great math question. It's also really hard. because establishing density properties of these representations, just given kind of abstract data about a category, there's some conjectures out there in math, especially from Eric Rowell, something called the property F conjecture. They're great questions, great math, but man, like getting progress on them is like really difficult. And on the other hand, 2 has not sort of received a ton of attention, but I think it's quite pertinent. And you know, if these charge measurements are fault tolerant, then why not use them adaptively? So, right, so that's the big question, but I told you I'm not going to do the big question today. So, right, but I'm going to do a warm-up. So I'm going to give you a theorem due to Greg Cooperberg that explains where the warm-up comes from. And so this warm-up tells you that if B is universal non-adaptively, so I allow braiding, but I don't do adaptive measurements, then the problem of evaluating the topological amplitudes or the partition functions on links is sharp P hard. So this problem, it takes a diagram of a link. So a link is like a knot, but with multiple components, like, you know, like a chain, right? A chain could have multiple things linked together, something like that. So this is a link diagram. And it's colored by, each of the strands of the diagram is colored by an anion. And in this setting, I'm thinking of it's colored by actually a simple anion. So the computational problem that's hard is taking this diagram and then computing you know, the invariant of the TQFT on that diagram, which will be some, we're computing this exactly. And so all of the data, they're algebraic numbers. So this thing is some algebraic number over Q bar, and you want to compute that algebraic number like symbolically. So in fact, this theorem, this is true even if instead of computing this exactly, we just try to compute it approximately with a multiplicative error. Sorry, I didn't write the conclusion. Sorry. So this problem is sharp P hard is the conclusion. So sharp P, if you're unfamiliar, is the counting analog of NP, right? So NP is something like, oh, given this graph, is it 3-colorable? Sharp P is like, oh, given this graph, how many 3 colorings does it have? Okay. And so Greg really didn't prove things at this level of generality, but if you go through the yoga, it's like pretty much, if you know, if you understand how his proof works, then you can prove this. And just for fun, I'll note that the proof uses Aronson's theorem that post BQP equals PP, so that you know, the universality from the braiding, like the very fact that thing's dense and universal is kind of telling you that the topological amplitudes have to be sharp P hard. And so this can be improved or modified. This is not written down anywhere. I don't think I would ever bother to write it down, a proof of this, but it's for context what I'm about to do. So the first modification is what I said a moment ago. So rather than computing it exactly as an algebraic number, it's also true for, so the sharp P hardness is true for, the conclusion here is for multiplicative approximations. And then it's also true for universality in the adaptive setting, except we have to modify what types of partition functions we compute. So here, it's really a link diagram colored by a simple anion. If we are in the adaptive setting, but it's possible adaptively. So if I'm universal adaptively, these invariants might be easy to compute. if I'm only looking at links colored by simple anyons. But if I look at more complicated topological objects, what are called trivalent ribbon graphs that are colored by non-simple objects, then we get Sharpie hardness. So I'll be happy to say what this is at the end of the talk, maybe, but for the sake of time, well, yeah, question.
Most interesting part of this theorem, like the sharp p-hard. I mean, it has to be hard, otherwise you can say you can sample from your circuit, basically.
Yes, yeah. So the way I interpret all this now is, I told you this theorem I'm using as a bridge to a warm-up problem. So, right, we're really interested in universality, whether adaptively or not adaptively. But if you're going to be able to answer that question, then you're going to know something about the hardness of the invariance. So we're going to change to the warm-up problem where we now ask, all right, forget universality, how hard is it to compute these invariants? Does that answer your question? Or maybe you were making a better point and I.
No, I just,
Yeah, okay, yeah, sorry. Yeah. I have bored brain, I guess. Let's see. So, yeah, so the moral, the too long didn't read of all this is roughly that B universal implies hard topological invariance. But we have to be careful about what type of topological objects we're computing invariance of in this paradigm. So, all right, I think I'm ready for the big grid now. All right, let's see. There's probably plenty of people in this room could answer a lot of these questions. Are abelian anyons braiding universal? No. Are easing anyons braiding universal? No. Are D4 anyons braiding universal? No. Are DS3 anyons braiding? No. DA5? Nope. No, not adaptively. Non-adaptively, they're not. No, adaptively. Fib, is that braiding universal? Fibonacci, yes, okay. All right, abelian anyons, are they universal with braiding and adaptive charge measurements? No. Easing. It's believed to be no, but if you ask Zhang Han, it's an open question. So I would say no, but with a question mark. So this is going to haunt me at the end of the talk. Okay. BD4, is it universal with adaptive measurements and braiding? Probably not, right? But if we don't know the answer to easing, why would we know the answer to D4? So I would say it's no for basically the same reason we don't understand easing. Sorry?
Maybe one more question mark?
Yeah, let's see. So what about the double of S3? Is that universal with braiding and adaptive measurements? Yeah, this is true. Yeah, Mo-Chin proved a version of this in the early 2000s, and then Sean Sway and Zhang Han and collaborator proved this as well. And it's been used recently, right? So for certain protocols. Okay, DA5 is also, and Fib, of course, is. So, okay, so now, so this is just about the universality question. So now what I'm looking at here, these are the warm-up questions, right? So like I have different types of topological objects. Here I'm looking at knots. So these are one component knotted things. Here I'm looking at links. These are multiple component things where the number of components can grow. And in these two cases, I'm going to only allow myself to color them with the simple enneon. But if I pass to links, I might also color them. Once I pass to links, I could also choose to color them with a composite enneon. And in some sense, it would be more interesting to put trivalent ribbon graph there because of this, but it's not. I don't want to get into what those are. And then finally, for closed string manifolds, you don't need to color them because you're summing over all colors in some sense for those things. Okay, so I'm going to go column by column now. So it turns out for abelian, any one of these things, if we're in an abelian setting, they're all computable in polynomial time. FP is functional polynomial time, right? It's not P because P is decision problems, but yeah. So easing, these are FP because they're Clifford circuits. But for a composite link, it's actually sharp P hard. If I color it by if a link colored by composites is sharp P hard. And same for 3 manifolds. Okay, DD4, it's kind of similar, but yeah, so this is an FP. This is not like written down anywhere, but it's using what I'm going to talk about in a few minutes. It's not hard to show. And similarly for links, well, okay, there are some cases here. Most cases I can prove to you, yes, this is an FP. There's a few lingering cases that I hadn't worked out. But, now if I look at D4 and I color it by a composite color, well, it turns out, maybe I'll use some, speaking of color, I'm gonna try to advertise the new stuff in purple. So I had color there. So this is also sharp P hard. Wow, that's a great color. That pops. Does everyone see that okay? Yeah, okay. And then this is also sharp P hard. We're in the home of Hagoromo. You get all the good colors. Yeah. So exotic. Okay, so double of S3. I would say this is also kind of probably in polynomial time for a lot of the simple colors in the double of S3, a lot of the simple anyons, I could prove this, and I'd have to think harder for some of them, right? So for the pure flux things, I could prove this. When you have dions, I could probably also prove it, but if you have mixtures, there's something to do there. So yeah, this is also FP probably. This is not known, so if I have a link with many components and I color the components by some composite anion, I don't know. I would guess this is sharp P hard. And finally, another new thing is that this is also sharp P hard. Although in some sense, you know, these are new in the sense that we now have proofs of them, although they would follow from this in some sense. But this, I haven't written down a proof of this, and I don't know that I'll ever bother. So, okay, now when we're in this setting, so, you know, we're going to talk about this stuff in a moment here. There's a lot that's already known here. So like in my thesis many years ago, I proved this is sharp P hard. And then that just propagates all the way down. And then for fib, it's also sharp P hard. And that propagates all the way down. So any questions about this table of examples? So one subtlety here is that when I say a composite color, we should really include that as part of the data with B, right? So which composite color? And I should do it here as well, right? Like, because, you know, we should, there's a question of, do I, you know, because for a link or not, I have to make this, it's not just the category, I need to tell you what anion to color it by. And so we should keep track of that. And what I'm asserting here is that for all colors, these facts are, right? For the algorithms, for the FP results, I'm asserting it's for all colors. And for the sharp P hardness results, I'm asserting that there exist colors. Because of course you could always use the vacuum color and then you have a trivial invariant. So, you know, the refined question, you have to keep track of both of those. Okay, and now let's try to extrapolate from that. So last year, so let me say in all of these settings, we expect sharp dichotomies. In the sense that, okay, like this universality question, I expect a sharp dichotomy in the sense that like either the category has universal operations or the operations are so weak you can simulate them in classical polynomial time. And similarly for these computational problems, either they're hard or they're NP. What I mean by dichotomy. And so, so this kind of line of thinking began with my grad student last year. So where we looked at a more general problem where when you're given the data of the fusion category B, you're given a bunch of elementary tensors, and you can imagine using those elementary tensors to allow yourself to build arbitrary tensor networks out of them. And what we proved is a dichotomy for contracting those tensor networks. So we proved that either it's Sharpie hard is or in FP. And this is, again, we're computing these tensor contractions. You're getting algebraic numbers at the end. It's all happening symbolically. Unfortunately, we didn't have any conditions. We didn't know how to separate the two. In part because, so we didn't know. We had a guess, like you would guess that, okay, abelian tensors are probably easy and everything else is hard. We don't even know if that's true though. But in some sense, I don't care because my colleague Cesar Galindo has proved a better result like a month ago. So this is new result. It's a mathematician in Colombia, works on tensor categories most of the time, but he's taken a liking to quantum information, kind of cool. So we fix our modular fusion category B. Then what he showed, all right, so he didn't get a dichotomy for the knot invariance. So the link invariance, he got a dichotomy for the closed three-manifold invariance. Okay? So this problem that takes a triangulation of a three-dimensional manifold to the value of its partition function, the 3 here just means it's a three-dimensional manifold, then this problem is Sharpie hard whenever B is non-abelian. And if B is abelian, well, we know that there's an efficient algorithm to compute the invariant. So we have the dichotomy. So yeah, so just saying in words here, right? So what we did was we harnessed dichotomy theorems that are known in computer science already. So what we used here wasn't a tensor network problem, but it's something not far off. It's called counting CSPs over the complex numbers. Yeah, so there's a known dichotomy there for that, and proved by Tsai and Chen. So these are Tsai Jinyi is a computer scientist at Wisconsin, and yeah, but their theorem doesn't have any constructive conditions. So it's like, yeah, these counting CSP problems are either easy or hard, but they don't know where to draw the line. On the other hand, Cesar, the way he succeeded, Tsai has another result about counting weighted graph homomorphisms. And there's a clean dichotomy where you have decidable conditions. And he was able to interpret that in terms of these tensor networks and win. So, yeah. Any questions? Yeah.
Is there an interpretation in terms of the topological computation of the simple knots? Like, do those correspond to like a restricted computations in which something happens?
Yeah. Like, you might have a bunch of anyons, but like their total world line has to be a single world line.
So like,
That's
it was like,
I don't know. Yeah.
Things and then if that
Yeah.
measure them, but like,
Yeah. So certain things wind up happening, like with fib, when you have the universality, you also have the universality if you only use braids that like permute the anyons around in your favorite way. And so once you have that, you can engineer that you always get a knot. Yeah. So for quantum computing, I don't know that these distinctions here and here make a lot of sense or that interesting, but for low dimensional topologists, it's worthwhile. Yeah. Yeah, what's going on here, like why a topologist cares about the distinction here, is that the first homology of a knot complement is very simple. It's just Z. But the first homology of a link complement is Z with a rank Z to the R, where R is the number of components in the link. And so that like you can get complexity for cheap reasons because the homology of this guy's big. And yeah. So if you can prove that like you're hard on knots, you're saying that like it's hard for reasons that don't have to do with the fact that the homology just happens to be big. Okay, so if that wasn't scary enough, then I'm going to do a little bit of a deep dive on the double of D4 now. Because this is one of the new, so yeah, so these purple things kind of follow, well, in some sense, there's a sense in which all three of these purple things follow from Cesar's result. But I'm going to give a proof of this Sharpie hardness for a different color. So like, if like this row always, hardness here always implies hardness here. If that color becomes what's called the Kirby color. But I'm going to give you a different color where this is still Sharpie hard. It's a simpler color. So yeah, so here's so a DD4 deep dive. So let's try to get our hands on this and get like an elementary proof of the Sharpie hardness for links. And so the fact number one is that if G is any finite group, and the anion I pick is the sum of all of the fluxes, I guess, the pure fluxes. These are the conjugacy classes of the group, labeled by conjugacy classes of the group, with the trivial representation of those guys' centralizers. So if I use this as my color, then to color the components of my link diagram, then the value of the partition function. So I'm going to denote my link diagram where all the components are colored by that, just like as L sub A. So this guy equals up to some fudge factor that isn't interesting. So this may not be true exactly, but it's close enough. The number of homomorphisms from pi1 of the complement of the link to G. Okay. And so since I'm low on time, I'm going to transport you to the bottom of the deep dive and just write out what this means in the case that G is D4. So counting this number can be set up as solving a system of equations of a specific structure over the finite field F2. And I'm going to tell you what those look like. So getting this count, I should say this is all the deep dive here. This is all joint with my students. I've had some undergrads and a grad student working on this over the summer with me. This is equivalent to solving the following system of equations. Or when I say solving, I mean counting the number of solutions to the following system of equations. So what's going to happen, L, right, my link has many components, right? I'll call the components K1, K2, Kn. So, I don't know, you can imagine a chain with n different links in it. Then the system of equations, I'm going to get one equation for each component. And that equation is going to depend on how that component, what its linking number is with the other components. And so this will look like is following. So you're kind of counting zeros of a twisted symplectic form over the finite field F2. This is mod 2. I'll put a 2 there. This is all mod 2, where these are these are certain vectors. So these xi, yi's, these are vectors over F2, so the two-dimensional vector space where F is just 0 and 1. So you're just solving some problem about weird symplectic pairings on vector spaces over the finite field. And now the fun fact is, I don't have time, so I won't draw the picture. It's very easy to prove. If you give me any symmetric integer matrix with zeros on the diagonal, I can give you a diagram of a link whose linking numbers kind of equal that symmetric, whose linking matrix equals that given matrix. Okay? And so what this means is that if you just allow like arbitrary ij coefficients here, so long as they're symmetric and 0 on their diagonal, you can realize any system of equations like this using link diagrams. And systems of equations like this are sharpie hard to solve. Okay. So this is like a direct proof that for that color, when D is D4, you get the sharpie hardness. Okay. So I apologize, that was a lot. I wrote a lot more, so maybe I saved you from that by running late anyway. So let me just make some final remarks. Yeah, maybe I'll write these things. Yeah, if I had more time, you would see cup product again. But if you're interested, I can show you after the talk. Yeah, so there's an easy sense in which this is coming from certain cup products. So yeah, so far, like the bulk of this talk, we're discussing dichotomies of exactly computing these topological invariants, but we could ask about dichotomies for approximate evaluation. This is maybe pie in the sky. This is something I've thought about quite a bit over the years and really just haven't made any traction on, is like, do these hardness results for these amplitudes have any implications for this TVV conjecture we heard about from Natalie? I'm actually not optimistic they do, but I want to throw the question out there because maybe someone has a better idea than I do. And then finally, how does all of this feed back to the original motivation of universality? And I told you easing was going to haunt us at the end of the talk. Believe it or not, we don't have enough information about easing stuff yet in the world. So I'll kind of throw a conjecture out there. I won't write it down, but we have to stare at these things and try to understand what's going on in the universality setting that isn't, how is like the universality dichotomy different from the evaluation dichotomies? And the key thing is understanding the difference between the group S3 and the group D4. At least I think the key thing is, this is where I'm headed. So what do we know about D4? It's nilpotent. And what do we know about S3? It's not nilpotent, it's solvable. What do we know about easing? Easing actually is a nilpotent modular fusion category. So there's a generalization of the idea of nilpotent group to nilpotent fusion categories, and easing satisfies that. So what one would expect is that in general, these invariants based on all of this, in general, exactly computing these topological invariants is going to be Sharpie hard whenever you have a non-abelian theory. But the universality is only going to show up when you have maybe a non-nilpotent theory. Although there's some subtleties here that's not captured by these examples, which is that easing and D4, not only are they nilpotent, they are class 2 nilpotent. There's higher nilpotency class groups that aren't solvable, or that aren't lower nilpotency class, like DD8, right? So the dihedral group D8, it's nilpotent, but it's not class 1 nilpotent. Well, it's not class 2, it's class 3 nilpotent. And so is the double of D8, does it have universal operations? Or no, the nilpotency, even though it's a higher nilpotency class, it traps it in efficient simulation. So I don't know, but I would conjecture that it's probably simulatable efficiently on a classical machine. And with that, I will stop. Sorry for going a little late. Yeah. So as the last speaker, I should also make a point to ensure that the organizers are thanked profusely. So thank you guys very much. This has been a ton of fun. I know I may be a little bit of an odd duck here at the end with the chalk talk and all that, but I've learned a lot. This has been an awesome event. So, well, yeah, so yeah, there we go. Cool. Yeah, so maybe we give them each a.
Oh, fantastic. Yeah, we still have time for a few questions
Okay.
there. People, some last questions for the. I was going to start with one actually about this like adaptive measurement. Is there like a limitation on what kind of these probe measurements you can do? Because you could kind of imagine you're sort of doing some non-topological thing that just introduces a magic state, and then you
Yes.
could distill it to become a good magic state.
So as far as I'm aware, the two precise types of operations I wrote down should be considered topological, and I don't think they can be used to inject magic.
But you can make any superposition and then braid it around and measure it, or
No,
just
no.
one but not
Okay, yeah, this is, yeah, so those particles I'm preparing, right? Like when I called that anion P, when I pull that probe anion out of the vacuum, right? Pulling that out puts it in a specific state, right? Because that Hom space, like P dual going to the vacuum, one-dimensional.
Okay.
So yeah,
So you kind of restricted that.
that's right. Yeah.
Good, good.
Although there is some question of like, that's a gauge choice. So yeah, a little bit.
Cool. More questions? We all happy? Maybe we should thank Eric again and take it
Cool. Yeah,
offline.
yeah. Thank you. Yeah.